Yeah.
So hello everyone. So it's my great pleasure to introduce Patrick Maillé. So Patrick is no stranger to this area. He's already been with Polytechnique, graduated in 2000, and then he came also to Télécom Sud Paris for a degree. Then he moved to IMT Atlantique, where he took an associate professor position there. Patrick also visited Columbia University in 2006 and Berkeley in 2014, 2015. So Patrick is mainly working on economic aspects in telecommunication networks, pricing, auctions, and it is our great pleasure today to welcome you for this seminar for the X. Please.
Thank you very much, Tiffany. And thanks for inviting me, to you and Andrea and Christina for their help. Hello, everyone. So today I'm going to be presenting some work that is joint with Bruno Tuffin, with whom I work a lot, and also with Yassine Hadjadj-Aoul and Maël Le Treust, who are also in our team. The name of the team is Hermine in Rennes. And so we are going to be trying to model and get some insights about the economics of network slicing. So if you know more than me about network slicing, any help is welcome to improve the models. So there's probably a lot to criticize. And so our goal is to try to understand and model network slicing from an economic perspective and try to have a look at what kind of regulation could be implemented and whether it's needed or useful or not. Okay, next step is to go to the next slide. Okay. So just a little bit of context. The generic context in wireless telecommunications is the next generation is much better than the current one. So kind of salesman generic discourse. So now is 5G is much better than 4G. Well, it's almost 6G is much better than 5G now. And so we're trying to get more into the details. So why is it much better? Because yeah, we're going to be able to serve much more demand. So with larger throughput, more users, new services will be possible, even those that have some specific performance requirements, such that very low delay. But yeah, again, it's a bit, we don't know what's under the hood here. So one question is, how can we do that? And an answer that we get is that slicing will solve those problems, will enable those new services by creating separating networks that will be tailored to the needs of the services that run over those networks. Okay, so we just separate logically the networks we have so that we can have some guarantees of service. And so we'll try to model that. And in particular, a question we can ask is, what are the associated business models that can be implemented on that? For example, if some provider has to ask some resource to create a slice, what prevents them from asking too much and take too much of the resource that would leave too little resource for the other services that would, or the other slices that we would want to create. Also in terms of economics, if we let network operators do whatever they want, doesn't it give them too much power about regarding the network? And so will they use that excessively and to the detriment of the users? Also, I've been working a lot with Bruno Tuffin on net neutrality. And so we had the reflex when we were first told about slicing that, well, it's completely against net neutrality principles. So what should we do about that? Should we do something or not? Or just say, okay, let's forget about net neutrality and just create those separate networks. And also another reflex we have is putting game theory everywhere. And so here, considering that we have many actors that are, of course, supposed self-interested. So we have the operator, the possible service providers who will create the slices or ask for slices. We have users. And again, our reflex is to consider that everyone will try to grab the largest part of the pie. So in this work, we try to build the first model and analyze it for the interactions among those actors, the operators, service providers, and users in the context of 5G and slicing. So we try to build that. So again, we are not specialists about slicing, so we try to understand the basic idea. And so far, what we understand is we have a large pipe, and the slice is just a sub pipe that you isolate inside the big pipe. So that would be you have some capacity, the global capacity that the network provider can offer, and some of it can be reserved and set apart to create a slice and will be devoted to a specific service. And so yes, that's how we will model slicing. So it's a very simplistic model. Again, suggestions for improvements are welcome. And we build a three-stage game between the operators, the possible service provider who will want to create a slice, and the users. So the story will be the operator, so the one owning the big pipe, will choose a pricing function for capacity. So then a service provider will be able to say, okay, I want to buy this amount of capacity and I will pay the price that is defined by that pricing function. So it could be linear or anything else. Then we'll have the one actor that we call the service provider that will be able to buy that capacity and to use that capacity to offer some premium service to the users. And then you will have users who will decide either to use the premium service proposed by the service provider or the basic service that is provided on what's remaining on the pipe, or no service at all if the service is just too expensive. Yeah, the second stage, I should also specify that the service provider has to decide at what price to offer its service. And so we have an interaction that we treat as a leader-follower game. That's also called the Stackelberg game, meaning that at each stage, we assume that the decision maker is able to anticipate how the other ones will react. So when the service provider buys its capacity and chooses its price, it's able to anticipate what the demand will be from users. And then similarly, at the higher stage, the operator should be able to anticipate what direction of the service provider would be. So again, that can be seen as a strong assumption. Yeah.
So there's the difference between operator and service provider.
Yeah, the operator is the one who owns the pipe, and the service provider will be renting or buying a subset of the pipe.
To sell it
to resell it, yeah.
Users.
Yes.
So it's a three body.
Yes.
And why,
Yeah.
why does not the operator do it?
We do that as well. Let's see what changes, but yeah,
Okay.
it can. Yeah, and since we are interested in regulations, we look at three different regulation scenarios. So the first one where there is no slicing allowed because net neutrality should be defended, and so forget about all this slicing story. The other regulated setting could be that, okay, you're allowed to, so the operator would be allowed to sell a part of its pipe, but we control at what price. And the last one is no regulation at all, so each actor can do whatever they want. And yeah, we will look at two different market structure. Either the service provider is an entity that is independent from the operator, or it's the same entity, like Francois was suggesting. Okay, and then we can do many more options. We could have one SP that could be integrated with the operator and another one, but that would be too complex so far. So we start simple. So if we summarize the story, we have this capacity C of the pipe. So that's my operator. Then it can sell some amount of capacity at a given price. So that's the price function that can be chosen by the operator. Then on the remaining capacity, the operator can sell some basic service. Yeah, and so that operator is an economic actor. So what he wants to maximize is its revenue. So there are two sources of revenue here. So there will be the service price that we note by QI for ISP. And there is the revenue from selling the resource to the service provider. And we'll see there is also a QI even if you use this pink service here. Okay, so that's the operator. The second player in our game will be the service provider who decides how much capacity to buy and at what price to offer it. And here in our model, we assume that the users still pay here the QI to the operator for the service, but there is a premium, so it's more expensive to use this service than the basic one. Okay, so that will attract some demand that we denote by the S from SP. And so its utility will be the revenue per unit of demand times the demand minus how much it costs to buy this capacity. Okay, so quite simple. And then we have users who have to choose between three options. So either the yellow service or the pink service or no service at all. And for that, we use a discrete choice model. Yeah, so we will just detail that just afterwards. But so the reference is we take no service. So we will say that the utility for that is 0. If you take the very basic service, you pay a price QI, and your utility will be decreasing with the number of people, with the load on that part of the pipe that we denote by D0. And for same thing for the pink service. So there is a different price, higher price, utility also subject to congestion effects. And just I have the the equations that we consider here.
Question
Yeah.
again. So on your slide.
Yeah.
So I'm trying to understand the utility and the congestion. So there is some randomness in the access to. I mean, some users choose basic, others choose premium.
Yeah.
And you would have like a queue with loss or something like that, and the utility would be.
Yeah, we take even simpler model than that. Well, it looks like this.
Okay.
Yeah, so we have the three utilities. So the reference utility is no service, so utility 0. And then, so that's the utility if you take the service, so that's the pink one, I think, the service from the service provider. So this is, well, I have to wait animation. So there is a part that is the kind of perceived throughput, like the quantity, the capacity per user, right? The capacity divided by demand. So that's the kind of capacity you have per user. Well, we take a increasing concave function of that. We take a log and with a parameter that can be interpreted as some sensitivity. And there is the monetary effect. So there is the price here. Q plus QI is the price you pay for that service. And we take log of 1 plus that. Again, with some parameter for sensitivity to price. And this is some random variable. So this is total price you pay. And to model the fact that not everybody has the same exact sensitivity or the same exact preferences, we add some kind of noise.
What happens is that if you get for the prime service or the pink one, then you don't divide by the number of users. This is the slicing, is that you have this rate.
Yeah, here is
alone,
just,
right?
yeah, it's among the guys on the pink service, this. So it's the capacity, the pink capacity divided by the number of users taking the pink service. So we have separate types. One with capacity CS and one with the capacity C minus CS. So it's like this. We have here capacity CS. The demand will be DS, so the demand number of users using that one. And we say, okay, people will be sensitive to the capacity per person somehow. Okay. Yeah, but it's not.
Because, so
there is no queuing
no,
there behind that.
I thought that the slice was that, I mean, you ask for, I don't know, 1 terabit and you get your terabit whatsoever. It's not shared with anybody.
Yeah, okay. But okay, here in the story we're telling, we're saying so it's the service provider who asks for the terabit, and then he wants to sell that to multiple users. Okay, so those are those multiple users that make up this DS. So there is no guarantee per user, because if you attract many users, they are still on this fixed size sub pipe, right?
I see. Okay, so the slicing is no guarantee, as I probably misunderstood, of getting something which is sort of completely separated from the environment and the presence of others. Slices are in your model traffic dependent, right?
Yes, but it will depend only on the traffic on that service.
On that service.
It will not be affected by how many people choose the yellow option.
But the slice doesn't guarantee, say, a rate or something.
The total rate is guaranteed. It's going to be a total capacity CS. But then if you have too many users choosing that, it's not a guarantee per user. It's a guarantee on the total.
You will control that by price. Okay. So
by
price.
Yeah.
That's the idea. Yeah, thanks.
Yeah. So there is the price effect and there is a congestion effect. So if there are too many people on that option, then it will become less attractive because the capacity you see is smaller. So we had this noise. Well, we did not invent this. It's a common practice in discrete choice models. And we do the same kind of modeling for the basic service. So same sensitivity to throughput parameter multiplied by the log of this capacity per person. So that's the remaining capacity on the pipe. So that's the size of the yellow pipe divided by the demand on that pipe and minus sensitivity to price times the log of 1 plus the paid price. And we add some other noise to avoid having everyone preferring the same option. So that's a way of dealing with that. And then what is done often with this kind of model is we assume that these noises have some specific distribution that they come from the Gumbel distribution, in which case we have an analytical expression for how demand should spread. They should spread proportionally to the exponential of the parts that are non-random. So proportionally to this part. So it will be 1 for the choice where you take no service at all because the utility was 0. It was the reference utility. And it will be the log of this. That will be the weight of the demand choosing option 0. That's the basic service. And that will be the exponential of that will be the weight for demand choosing the service provider's service. Okay, so we have this kind of thing. So just to say that demand will be spread proportionally to these exponentials of the non-random parts. Okay, so the demand on the service provider service should satisfy this. So it represents this weight of the total mass of users. And yes, I should say that we assume the total mass of users of 1. So thanks to this discrete choice model, we have this kind of thing. But what is specific here is due to congestion effects, there is some DSP here. So we do not have directly the solution. It's kind of a fixed point. But it's not too difficult to show that there is a unique fixed point. Yeah, one thing I should have said as well is maybe just coming back to the drawing here. To keep the model simple, we didn't. You saw there was no really a difference in the provided service between the yellow service and the premium service, right? They just differ through the price. So I don't know if you've heard about the Paris metro pricing mechanism. No, not everyone has, probably. Sorry?
Early papers a long time ago.
Yeah. So yeah, it's this pricing mechanism that used to be applied in the metro in Paris. So where you had first class and second class. And so the price is not the same, but the cars are exactly the same. But the first class is more expensive because it will be better because it's more expensive. So there will be less people. And that's the idea here is, okay, this thing is going to be more expensive, so it should attract less people. So service should be better. So that's the simplest way of modeling some differentiation, because otherwise we would have to enter into some, I don't know, what specific types of protocols or specific services. And we try to keep things a bit abstract. But yeah, so we are basically implementing a Paris metro pricing scheme here. Just, it's supposed to be better because it's more expensive. So there will be less congestion. Okay, so that's about how far we managed to get analytically. We were able to, so here we turn to the analysis of the game. So we managed to show that there is um, a unique equilibrium for any configuration of the capacities and prices. And so it's a fixed point of the equations we saw before. Because we are trying to solve the game, and the method is backward induction. That means we just focus on the last stage, that is the user stage. Given any prices and capacity, we trying to solve the equilibrium. Then we want to use that on the stage above to say, okay, knowing how to compute the equilibrium and therefore knowing how people will react, how should I choose my premium capacity and premium price to maximize my revenue? And then above, knowing how the service provider reacts, how should the operator set its price, for example. Okay, so user choices, we managed to show that there's a unique user equilibrium, and we showed a very simple method to compute it. But then, as early as the second stage, we did not manage to solve analytically that game. So we did some numerical analysis. So here, the difficulty is to choose parameters. So we try to fix some parameters, but this can be criticized a lot. Well, what we liked is, looks like there is some optimum somewhere. So this is the revenue part from selling the service. So without having to pay the capacity, and this is the total utility of the service provider. So this is for any fixed capacity that you buy. You have an optimal price at which to charge the service, the premium service. And this is because you have two variables to fix, the price and the capacity you buy. So this is as a function of the capacity you buy. When you take the optimum price for that capacity, this is your revenue if you are the service provider. And yeah, we tried with a bunch of parameters, and it had this nice look where you have an optimum. Okay. Sure.
So the on the left,
Yeah.
so why do you consider only the price, the service? So this is the utility of the service provider, not the network operator, right?
Yeah, exactly.
Okay.
Yeah. It was the second stage is the service provider, and then the last or first, if you say it's the one that makes its decisions first, then you have the operator. So we studied last in this backward induction method. So now the operator decisions are at what price to charge for the basic service and what pricing function to apply. So since we are already with numerical analysis, so we again do numerical analysis. So this is just an example. So with a given pricing function, what happens when you vary the price of the basic service? Again, looks quite nice. There's an optimum that we can find numerically. And we start to see that it's not that easy to maximize numerically, and it's not that smooth, but so that's so here, this first curve is when you move the price of the basic service, what's the revenue of the ISP, so of the operator? What's the capacity that you're going to sell? So if you increase your service price, there is an optimum of, well, it's not optimum, but there is an amount of capacity that will be sold to the service provider. And okay, we see this is the resulting equilibrium. So then we fix the QI, okay, the price of the basic service. Then the service provider reacts, setting its optimal premium charge and uh, capacity CS, and then users react, and then based on that, we can estimate some service quality. That's the ratio between capacity and demand. That's what we call service quality, right? That was in our utility. We had some part depending on the service quality and some part depending on the price. So here we see some difference. The premium service is better in terms of this ratio than the basic service. And again, that's just because of the difference in price, thanks to this Paris Metro pricing mechanism. Okay, just to describe the regulation and market structure scenarios we had a look at. So, okay, we fixed some kind of arbitrary pricing function. We wanted something convex, so we took A times, so some parameter A times the square of the capacity. Again, this can be changed. So, different market structures and neutrality regulations. So first, no regulation. The operator can choose this parameter A. Well, still the form of the function was imposed, but that's because we are not good at optimizing over functions. We prefer optimizing over just one parameter. So we choose those two parameters, this A in the pricing function and this price of the basic service. Then the SP chooses the capacity and the premium price, and then users subscribe. That's no regulation. The second case is when the SP is actually the same entity as the operator. So that's the vertical integration scenario. So there is no really some price exchange between the SP and the operator because it's the same entity. So you just have to choose some basic service price, some premium service price, and some capacity for the premium service. The scenario that we call neutral is the one where slicing is not allowed. So there is no service provider, no slices, just the full capacity, only the basic service. So here, this is easy to optimize. There's just one parameter, just the price of the basic service. And then in terms of price regulation, we could have a look at what happens if there is a regulator that imposes the choice of this parameter A and the choice of the service price. So what would be the goal of that regulator? That would be to maximize how users are happy, how happy users are. So that's the measure we call user welfare. That's some cumulated utility of users only. A weaker regulated scenario would be where the regulator just chooses the parameter A, but lets the operator choose the price of the basic service freely. And then we had the no regulation setting that was already mentioned above. Okay, and so we can run some CO Python with some bunch of parameters, and we can get some things like this. So we have our 5 scenarios, and this is the kind of things we obtain. So what is the parameter of the pricing function for the capacity? The price of the basic service, the price of the premium that you have to pay for the improved service, capacity that is used for that slice, the demand on the premium service, the demand for the basic service, the revenue for the service provider, the revenue for the operator, and user welfare. That's, again, aggregated utility of users. Okay, so those are maybe not completely satisfying because we are very small values for the number of people taking the premium. Only in the vertical integration, we have some significant demand on that service. But just to give an example of what kind of things we can say, if we focus on user welfare, for example, so just the last column. So you want people to be as happy as possible. So that's what you focus on. And you see there's a huge difference here. That's this line that is much higher. User welfare is much higher than all the other scenarios in which it's very close. But this scenario is the fully regulated one where the operator does not do what they want. And in particular, the regulator would impose some free service. Even the basic service would be free. So, okay, we can understand it could be good for the population. Maybe the regulator would not be happy with this kind of regulation, but that's something that the model tells us. We can also notice that unregulated and weakly regulated scenarios are exactly the same here for our parameter models from the point of view of the revenue of the operator. There are some small differences elsewhere, but here up to 4 digits, we have the exact same revenue for the operator. There's for the remark before, the suggestion was, okay, maybe instead of imposing a price of 0, if we could just put a cap on the price, maybe seeing that the optimal for if we let them choose whatever they want would be between 5 and 6. Maybe if we put a cap to, I don't know, 4 or 3, that could be better in terms of user welfare, but still acceptable by the ISP. Okay, for this remark in yellow, the ISP is indifferent. And if we look at user welfare again and forgetting about this fully regulated scenario, the second best one would be this vertical integration, where it's the same entity that offers the basic and premium services. So it's slightly beneficial. Well, it's not huge differences. You see, the values are very close. So not sure it's sufficient to advocate for vertical integration. And so of course it's the best option for the revenue of the ISP because it has no competitor and it can add extra revenue by creating this premium service, but it's also the best for user welfare. Okay, so this is just to see, what was maybe not completely satisfying was the huge premium we have to have here. So maybe the model can be refined. We see that you have to pay 5 for the basic service, and you have to pay an extra 18 or 19. So that would make a total of 24, 25, just for or 23, 24, just to get to this first class service. Okay, so just to conclude, so we aimed at building some simple model to represent the interactions that occur in 5G in the context of slicing, taking into account 3 types of factors and even a 4th if we count the regulators. Okay, the methodology is what we do a lot with Bruno is creating a game and trying to analyze it. And okay, in terms of future work, it'd be nice to have some realistic parameters. We tried a bunch of parameters and took the ones that we liked, but it's maybe not the best method. It's difficult to model. Well, we don't know exactly how to model the fact that there are different services on each slice. what we did is one extension we did is have two types of populations, with one population being more sensitive to this ratio, but that makes two more parameters, the proportion of each of those population, and the new parameter, the new sensitivity to quality of service. So more parameters to fix. But we have an extension of this work doing that. Other extensions would be having more than one service provider. So we could have several service providers. They would be in competition to buy parts of the big pipe. And also if they offer similar services, then it would be in competition to attract users as well. And for so far, our models also had just capacity, just the pipe. But we are aware that networks are more complicated than that. And again, the model is already too difficult for us, but okay, we can try to extend it. And yeah, we did not have background traffic on the network at all, that we could not control. We assume that all the traffic was choosing according to this discrete choice model. So yeah, then this last one we did a small step toward considering it, having heterogeneous users. And that would be it for me.
Any question in the room? Yeah, Sebastian?
So, first question is, why start with two classes? The 6 classes, 8 classes.
You mean more like the Paris Metro pricing with a third class?
Yes.
Yeah. It will be even more heavy. It's already long to get these curves like this. You see, they are not smooth because it's very long, because it's really several stages of optimization. So yeah, I don't know. My guess would be it would be kind of similar, but yeah, that would be nice.
Another question is, somehow it would make sense to use some kind of auction system. Okay, so each user puts a bid on how much he wants to pay.
Yeah.
And then the service provider takes the top 20% bid and gives them half of the capacity. And the lower 80% bids only gives them one half of the capacity. So if you put above the others, you enjoy better service, and otherwise you have lower service. So would it lower the price, higher the price?
Very difficult to anticipate. But yeah, auctions are very. We have worked a bit on auctions with Bruno for congestion pricing. There are many mechanisms that you can implement. Yeah, with auctions, what is nice with auctions is that you can have some provable properties like incentive compatibility. You don't have an interest in lying to the mechanism. So yeah, we could do something like this. I know we did fit into slicing, or you would auction for the slices. Maybe you could do auction among service providers.
No, it's 50-50, but the service provider could choose, okay, for 60%, it would be the lower 80%, and for 40%,
Yeah. Yeah, we could have the same two sub pipes and say, okay, only I will not allow more than this demand on the premium service, and I will take the highest paying users. Yeah, can be interesting.
Then there could be some dynamic if you get some. The auction would be valid, say, for 1 month, and then the month after, you can revise your auction
maybe to be promoted to the next class, or maybe you believe you are paying too much with respect to.
So you mean here that would be the operators or the service providers who are bidding for the slice, right? Yeah, that could be nice. Yeah, thanks.
Yes, I have a comment or a question. Now I think hearing this answer, I am better understand the reasoning behind this. But what puzzled me since the beginning was this fact that the service provider gives exactly the same service than the operator. So in my understanding of slicing was that I give you a slice to you, service providers, so you can do something with that and provide a service that the operator can provide.
Yeah, but I don't know how to model that. Or we could add some. Oh, sorry, go ahead.
So, option that the user has to go back to the operator.
Yeah.
The yellow pipe doesn't want to pay the price for the pink pipe, but in reality, I don't think this is what happens. But in reality, I subscribe.
Yeah,
I subscribe
they
to
had
the
this.
service because I need it. Otherwise, it's pricing of the operator that decides how to sell their bandwidth. Which would be the case where you have the service provider embedded in the. I don't know. Struggling a little bit to.
Yeah, to get convinced by them.
My understanding of slicing with the model you showed.
Yeah, another thing we thought about is, probably maybe depending on the service you want to use, maybe there are just only one slice offering that service, so you don't really have a choice.
So
that would be the kind of dedicated slices. You want to do some streaming. You don't have a choice between basic and premium. You have the streaming slice. That could be a different, slightly different model, but yeah, we have thought about that. But yeah, it's not what we're doing here. Could be interesting as well.
And so the other thing that was puzzling me was why slices would be against net neutrality, but it all boils down to this.
Because the principle of net neutrality is all packets or all flows are treated the same.
Yeah, if the two give you the same service, yes. Now I see your point.
But here, even with this model, they would not be treated the same because there is a higher throughput offered on the more expensive line, on the more expensive pipe.
Slice provide a service that it wouldn't exist otherwise.
Yeah, then maybe it's not a problem.
Okay.
Technical question on this noise. You took a very specific, you say gumble?
Gumble, yeah.
And so what is the technical reason and how is the structures that you find dependent on the this or that distribution for the fluctuation?
Yeah, I think this distribution has the nice property of giving us some analytical and simple expression of how demand will spread, because each individual user has the choice between these three options, so this utility, or zero. And with that noise, and then each person compares those three values and takes the one with the largest utility. And so when we have this specific distribution, you end up with a nice spreading of the demand between the choices that is proportional to the exponential of these points. But if we do with Gaussian or any other distribution, I guess it will be a mess, and it will. Well, it will be a different expression for how in the end the users will spread.
I see. And so, what physical justification can one give of choosing a Google, except that
except that it's convenient? I don't know. It's mathematically convenient for us. And we are the first one doing them, but
What is the shape of this kind of distribution? I don't know.
We can have a look. What's the look?
People in econometrics use this without asking.
Yeah, but it's good to ask. What's the looks like this? Looks nice. Yeah, it's not. There are two parameters, so we take I think 1 and 1, and in this here it's not symmetric, but I think with 1 and 1. Yeah, so this is. Yeah, the standard. So we take the standard one. So mu is 0, beta is 1. In which case exponential of minus. So that's the CDF. Do we have the PDF? Yeah, the PDF is here. So yeah, I have no good answer other than the other ones are doing it as well. Yeah, but no, it's a good one.
One more question? Yeah.
So, the pricing hypothesis, etc., are so works in case of monopolistic owner. Like road pricing, you can do because there is one owner of the roads, it's the state. Here we are assuming that there is one network that is monopolistically controlled by one entity. And so people do not have any choice.
You're right. We could also add another or two other operators.
If an starts to set prices in order to maximize its utility, me as a user, I would not go neither in the basic part.
You just go to competition.
I will go to the second.
Yeah, you're right. So more actors to introduce into the models. Yeah, right.
Some question on the bridge?
On the
remotely?
Remotely.
No, thanks.
Okay.
I have another one.
Go ahead.
The last one.
No,
I ask the other people have some questions. Yeah.
I do have a question. Because after you show that the Gamba distribution is log of exponential, right?
Yeah.
Then I wonder if you take the log.
Yeah.
If you take the exponential of everything.
Yeah, exponential of this. Yeah.
So it's kind of the multiplication or division of the throughput and price.
Yeah. We have the ratio here. It looks like this. This is the exponential of the, and that's also a reason why we took logs here and here to have something not too ugly here.
Sense.
Very small. So sometimes you consider the welfare, the user welfare.
Yeah.
If you consider the social welfare, that is user plus operator.
Yeah.
What was the best solution? If you took
we did not do it when difficulty is it is in terms of units, because here you see it's difficult to have some kind of units here. We have the prices are monetary in units, but we take the logs, and when we define user welfare, we take the average over all the populations of those utilities. That is the average of the max of USP, U0, and 0. And so we would have to do some conversion to compare that to the revenues of the actors. So, yeah, we did not do it because we don't know really. We're not sure how to do it.
Okay. So thanks again.
Thank you.
I don't get it.